Dear students, in this section we are going to study the fluid dynamics. Now, what is a fluid? The fluid means the substance which can flow. We know both the liquid and gases have the property to flow, so they are comprehensively called fluids. The fluids are everywhere around us. Earth has an envelope of air, and also the 2/3 of its surface is covered with water. And also water is essential for the existence of life on the earth. And also our body is mainly constituted of water. So what is an ideal fluid? An ideal fluid is that fluid which is incompressible and non-viscous. Incompressible means we cannot compress it. That means its density cannot change. The density is uniform at every point in the fluid. And the non-viscous means there is no internal friction inside the fluid. The liquids are approximately incompressible in most situations. And generally we think about the gases. The gases usually we are considered as compressible because there is a large space between the molecules of the gas. But if the pressure difference from the one region to another are not too great, then we can also consider the gas as an incompressible one. Okay. Now when the fluid flows, we consider the fluid motion is as a layer. That means each layer of the fluid, in each layer, the fluid particles are moving one by one in a line. So according to the nature of the motion of layers of a fluid, we divide the fluid motion into two types. One is the streamline flow and another is the turbulent flow. We can see that in the figure, in the upper figure we can see the fluid flows as layers, and the layers are not crossing each other, and they are flowing along a very smooth path such that the different particles never cross each other. So that is the streamlines, they do not cross. So such a flow is called a streamline flow, or laminar flow, or the steady flow. Okay, in steady flow, the velocity of the fluid particles at a given point is same irrespective of time. We know when the fluid flows, whether it is a streamline flow or turbulent flow, its velocity may change. But in the case of streamline flow, the velocity at a particular point. So when every particle crosses that point, it should have the same velocity. Okay, that is the particularity of the streamline flow. So you can see the turbulent flow. The lower figure you can see the turbulent flow. In turbulent flow, the flow is very much irregular. That means the streamlines are crossing each other. Why this happens? Because at a given point, every particles of the fluid may have a different velocity. The velocity is not a constant. So this type of flow is not steady or not laminar. So they are called a turbulent flow. So when we consider the velocity at above a critical speed, the streamline fluid flow becomes turbulent. So the turbulent flow is an irregular flow characterized by small whirlpool-like regions. The turbulent flow is very difficult to deal mathematically. So at the present, we are limiting our discussion to the the streamline flow or the steady flow. So when we consider the flow of the water from a tap, initially there will be a very smooth flow of water when we gently try to open the tap. This smooth flow can be treated as a streamline flow of fluid. But the steady smooth flow is getting narrower as the distance from the opening of the tap increases, and at last you can see the flow becomes irregular or turbulent. Okay. So let us see some of the differences between the streamline flow and a turbulent flow. So it is a streamline flow. It is a steady, smooth, regular, one by one flow of the fluid particles. At the same time, in the turbulent flow, the flow of the particles is irregular and in a zigzag manner. When we consider the speed of the fluid motion in the streamline flow is lower than a critical velocity. So in the case of turbulent flow, the fluid motion, the speed is always greater than the critical velocity. So when the critical velocity fluid is the velocity above which the flow becomes irregular or turbulent. And the third, the fluid layers do not cross each other in streamline flow, but they cross each other in turbulent flow. And the particle reaching in a given point in the path of a flow have the same velocity with time in the streamline flow, but the velocity at a given point is different at a different time in the case of the turbulent flow. But these are the main differences between the streamline flow and the turbulent flow. As we have discussed, we are discussing our discussion on the streamline flow. And also, we are discussing the fluid motion in the case of the ideal fluid, because in the real situations, the flow of the fluid is most of the flow is not a steady flow. It is a turbulent or it is irregular flow. So we are now concentrated on the fluid which is the ideal fluid, the motion of the flow of the ideal fluid, which is incompressible and non-viscous. But practically, the fluid is somewhat incompressible up to an extent. But it will have some internal force between the fluid layers against the flow. So we cannot neglect the viscosity of the fluid. Even though we say we are talking about the ideal fluid, we know ideal fluid should be non-viscous. But when we practically thinking, we cannot neglect the internal force between the fluid layers against the flow. That is, we can neglect the viscosity of the fluid. So there is a physicist, Osborne Reynolds. He observed that the turbulent flow is less probable for the viscous fluid flowing at a low rates through a pipe. And he found that, or he defined a dimensionless number that has a vital role in predicting whether the liquid has a streamline flow or turbulent flow. This number is called the Reynolds number. So from the Reynolds number, we can identify whether the flow is streamline or turbulent flow. And he defined the Reynolds number as Re is defined as the ratio of the internal forces to the viscous forces within flowing fluid. That is, Re is equal to inertial force divided by the viscous force. And he found the Reynolds number depends on so many parameters, and it is given by Re is equal to rho Vd by eta. Rho Vd by eta. Here rho is the density of the fluid flowing with the speed v. d is the diameter of the pipe, and eta is the coefficient of viscosity of the fluid. And he discovered that for the streamline flow, the Reynolds number is less than 1000. And for when the Reynolds number is between 1000 and 2000, the flow is unsteady, because whether that flow is lies between streamline and the turbulent flow. So when the Reynolds number is greater than 2000, the flow is turbulent flow. So from the Reynolds number, we can predict the flow is whether the flow is streamline or turbulent. Now we come into the continuity equation in the fluid dynamics. So let us see some example. നമ്മൾ വീടുകളിലൊക്കെ നമ്മൾ ഗാർഡനൊക്കെ നനയ്ക്കുന്ന സമയത്ത് നമ്മൾ സാധാരണ ഒരു ഹോസ് ഉപയോഗിച്ച് നമ്മൾ ചെയ്യാം. നമുക്കറിയാം ചിലപ്പോൾ ചില ചെടികളൊക്കെ ഗാർഡന്റെ അങ്ങ് അറ്റത്താണ്. നമ്മുടെ ഡയറക്റ്റ് ആയിട്ട് നമ്മുടെ ഹോസ് അങ്ങോട്ടേക്ക് എത്തുന്നില്ല എങ്കിൽ നമ്മൾ എന്ത് ചെയ്യും? നമ്മൾ ആ ഹോസിന്റെ ഒരു എൻഡ് നമ്മൾ എന്ത് ചെയ്യുന്നു? തമ്പ് ഉപയോഗിച്ച് പാർഷ്യലി നമ്മൾ ക്ലോസ് ചെയ്യും. പാർഷ്യലി ക്ലോസ് ചെയ്ത് കഴിഞ്ഞാൽ എന്ത് സംഭവിക്കാം? The water stream can reach the longer distance. Okay, this is happen according to the continuity equation. Let us see what is the continuity equations. Okay, so for that, let us consider a pipe of varying cross-sectional area through which an incompressible and non-viscous fluid, that means ideal fluid, flows. So you can see at the end of P, the area cross section is A1, and the velocity of the fluid at that section is V1. So at the other end Q, you can see the area cross section is A2, and the velocity of the fluid particles at that section is V2. Okay. Now, if rho is the density of the fluid, and considering the flow of the fluid through a pipe for a time delta t. So you can see, so let us consider the flow of the fluid for a time delta t. So in a time delta t at the section P, the fluid displaces a distance delta x1. Similarly, at the end Q, the fluid displaces out through a distance delta x2. Okay, then the distance traveled by the fluid at a point P is equal to, we know the velocity is, the speed is equal to the distance by time. So the distance is equal to velocity into time. That is, at the section P, the distance equal to v1 into delta t. Now, what is the volume of the fluid entering the tube at the point P, at the section P? That is equal to the area cross section into the distance. That equals the volume. That is A1 into V1 into delta t. So if rho is the density of the fluid, then we know density is equal to rho is equal to mass by volume. Okay. So if we know the volume, then mass is equal to density into volume. So in the second row we have the expression for the volume. So therefore, and rho is the density of the fluid. Therefore, the mass of the fluid entering the tube at the point at the section P is equal to density into volume. That is rho into A1 V1 into delta t. Similarly, the mass of the fluid entering the tube at the point Q, we can calculate as before. That is equal to rho into A2 V2 into delta t. Okay, but we know the total mass of the fluid entering into a pipe through any cross section should be equal to the total mass of the fluid coming out of the same pipe through any other cross section at the same time. Here, so in a given time interval, total mass of fluid ആണ് enter ചെയ്തിരിക്കുന്നത്. Three total mass of the fluid എന്ത് ചെയ്യണം, that should be coming out. Okay, so we can equate So we can equate the two expressions, that is rho into A1V1 into delta T should be equal to rho into A2V2 into delta T. Here, this is in accordance with the law of conservation of mass. Okay, so here the densities are the same, we can cancel out, and delta T, so we consider the flow of the fluid in at the same time. So delta T can be also cancelled out. So the remaining part of the equation, that is A1V1 equal to A2V2. A1V1 is equal to A2V2. That is A1V1 is the product of area cross section and velocity at the section P, or at the section we can denote by 1. Then that should be equal to the product of area cross section and velocity at any other point, that is say point 2. That is the product of area cross section into V, that is velocity, that is A into V equal to constant. Okay, now this is the equation of continuity. Okay, so the equation of continuity in the fluid dynamics states that when an incompressible and non-viscous fluid moving with a steady flow through a pipe of varying cross-sectional area, the product of area cross-section and velocity of the flow remains a constant at every point in the pipe. Okay, that means when the area decreases, A into V equal to constant. So when the area decreases, the velocity of the fluid flow must be increased to maintain the constant, and also the vice versa, because when the area increases, the velocity of the fluid flow should be decreased. Okay, we know the product AV, A into the velocity, the area cross section into velocity equal to constant, and this product is equivalent to the statement that the volume of the fluid that enters one end in a given time interval should be equal to the volume leaving the other end of the tube in the same time interval, provided if no leaks are present. Okay, and also you can see that the product A into V, which is dimensions of the volume per unit time, and it is called that is volume flux or the flow rate. So it is actually the volume per unit time, the volume of the fluid flowing out in unit time, that is the product A into V, and sometimes it is also called the volume flux or the flow rate. Okay, and you can see the examples. The first example we can already discuss. In order to bring the water to a more distance during the time of gardening, wetting the garden, you can say we are just pressing the thumb. So when you press the end of the hose partially with the thumb, we are actually decreasing the area cross section. So according to the equation of continuity, the velocity should be increased. So the velocity of the water flow should be increased, and so that it can reach the more distance. Okay, and also when we consider the motion of the water from a tap, you can see as the water increases, as the water coming out and it travels more distance, the velocity of the water particles will be increased, because that is due to the acceleration due to gravity. Okay, so the velocity increases. So according to the continuity equation, as the velocity increases, the area of the cross section of the fluid flow should be decreased. So that is why the flow become narrower when it is travels more distance from the tap. Okay. If the velocity is further increased, beyond the critical velocity, and then the flow become irregular or turbulent. Now let us see what are the different types of energies associated with a fluid flow. We know first one is the kinetic energy. Kinetic energy is due to the motion of the fluid particles. Okay, we know the during the fluid flow, the particles of the fluid are in continuous motion. So there is some kind of energy associated with that due to the motion of the fluid particles. So that energy is called, we know, the kinetic energy. And if m is the mass of the fluid flows with the velocity v, then kinetic energy is given by half m v square. Half m v square. Okay. So in terms of the density, suppose rho is the density of the fluid, then in terms of density we can express kinetic energy is equal to half rho v square. Half rho v square. The mass can be replaced with this volume and density. So mass is equal to mass by volume is the density, so mass equal to density into volume. For the unit volume, so m can be replaced by rho into v, so that it can be, so for the unit volume divided by v, so we have half rho v square. Okay. Now another type of energy associated with the fluid flow is the potential energy. Okay. Here it is the energy of the fluid by virtue of its position is called the potential energy. Okay, we are already familiar with this potential energy. Suppose it is when for a given mass of a fluid m, it is at if it is at a height h from the ground, then potential energy is equal to mgh. Is equal to mgh. As also as in the case of the kinetic energy, in terms of density of fluid, the potential energy is equal to rho gh. See here, for the unit mass, for the unit volume, not the unit mass, for the unit volume, the potential energy is equal to rho gh. There is another type of energy that way you can see. Unlike in mechanics, there is a new kind of energy can be associated to a fluid called the pressure energy. That is, this energy is due to the action of the fluid molecules to any substance immersed. We know നമ്മുടെ ഫ്രണ്ട്സിനും കൂടെ നമ്മളിപ്പോൾ നീന്താൻ പോവുകയാണ്. നമ്മൾ കുളത്തിലേക്ക് നമ്മൾ നീന്തുന്ന സമയത്ത്, ഡൈവ് ചെയ്യുന്ന സമയത്ത് നമുക്കറിയാം വളരെ ഈസി ആയിട്ട് നമുക്ക് വെള്ളത്തിനുള്ളിൽ കൂടെ നിങ്ങളുടെ ഫ്രണ്ടിനെയോ അല്ലെങ്കിൽ ഏതൊരു ഒബ്ജക്റ്റിനെയോ വലിച്ചുകൊണ്ട് പോകാനായിട്ട് വളരെ ഈസിയാണ്. നമുക്ക് അത്രയും ഭാരം നമുക്ക് വെയിറ്റ് ഫീൽ ചെയ്യുന്നില്ല, അല്ലെ? അതേസമയം വാട്ടർ ലെവലിന് മേലേക്ക് നമ്മൾ വന്നു കഴിയുമ്പോൾ നമുക്ക് അതിന്റെ ആക്ച്വൽ വെയിറ്റ് നമുക്ക് ഫീൽ ചെയ്യുന്നു. അപ്പൊ അതിന്റെ ഉള്ളിലായിരിക്കുന്ന സമയത്ത് ഈ വെയിറ്റ് ആക്ച്വലി വെയിറ്റ് ഉണ്ട്, അല്ലെ? ബട്ട് ആ വെയിറ്റ് നമുക്ക് കുറവ് ഫീൽ ചെയ്യുന്നുണ്ടെങ്കിൽ ആ വെയിറ്റ് ആരോ ഷെയർ ചെയ്യുന്നുണ്ട്, അല്ലെങ്കിൽ അതിന് ഈക്വലന്റ് ആയിട്ടുള്ള ഫോഴ്സ് അവിടെ ആരോ പ്രയോഗിക്കുന്നുണ്ട്. ആ കൊടുക്കുന്ന അതാരാ ഫോഴ്സ് പ്രയോഗിക്കുന്നത്? ദാറ്റ് ഈസ് the fluid molecules. Okay, so when an object is immersed in fluid, the fluid particles from all directions are exerting a force on that substance. Okay, so there is a net force acting on acting by the fluid molecules from all sides, and this net force is called the pressure. Okay, so this pressure is applied by the fluid molecules can do work. That is to carry the object for us underwater. So the fluid is doing work, and we can say it possesses some energy, some type of energy, and this energy is called pressure energy. This energy is called pressure energy, and we can have an expression for the pressure energy. If P is the pressure and m is the mass of the fluid and rho is the density of the fluid, then the pressure energy is given by mp by rho. mp by rho. Here m is the mass and rho is the density, and p is the pressure. So for the unit volume, we can also rewrite the equation as pressure energy is equal to p. Pressure energy is equal to p. Okay. So there are the three types of energy associated with a fluid flow. That is kinetic energy, potential energy, and the pressure energy. According to the continuity equation, the speed of flow can vary along the path of the fluid. So what about the pressure? The variation of pressure of flowing fluid depends on height as in the static situation, and it is also depends on the speed of flow. So we can derive an important relationship between the pressure, flow speed, and the height for the flow of an ideal fluid. And this is done by the Bernoulli, and that theorem is called the Bernoulli's theorem. So നമ്മളൊരു കാര്യം ചെയ്യാം, നമുക്കൊരു നോൺ ഏരിയ ക്രോസ് സെക്ഷൻ ഉള്ള ഒരു ട്യൂബിൽ കൂടെ ഒരു ഗിവൺ ഫ്ലൂയിഡ് ഫ്ലോ ചെയ്യിക്കുകയാണ്. ആ ഗിവൺ ഫ്ലൂയിഡ് ഫ്ലോ ചെയ്യിക്കുമ്പോൾ വി ഹാവ് ടു ഡു സം വർക്ക്. നമുക്കറിയാം, നമുക്ക് 3 തരത്തിലുള്ള എനർജീസ് ആണ് ഒരു ഫ്ലൂയിഡ് ഫ്ലോയുമായിട്ട് ബന്ധപ്പെട്ട് വരുന്നത്. അപ്പൊ അതുമായിട്ട് ബന്ധപ്പെട്ട് നമുക്കറിയാം വർക്ക് എനർജി തിയറം. ഓക്കെ, അപ്പം ആ ഒരു ഫ്ലൂയിഡ് ഈ നോൺ ഏരിയ ക്രോസ് സെക്ഷനിലെ ട്യൂബിൽ കൂടെ ഫ്ലോ ചെയ്യുന്ന സമയത്ത് these 3 types of energies are there. So they have some work done. So this work and energy are related, we know. So by using the work energy theorem at the 2 sections of a pipe with a different height. So let us see in the figure. We can see the 2 sections. One is x at x. That section is at a height h1, and the area cross section at that section is a1, and the pressure at that section is p1, and area the velocity of the fluid is at v1 through the fluid flow. So let's have a relation connecting these 3 types of energies. So from the work energy theorem, we can equate the work and energy, the 3 types of energy. So when we do, we can have this expression like P2 minus P1 into V equals half m V2 square minus half m V1 square plus mgh2 plus mgh1. So from that, when we divide every term by the volume, so P2 minus P1 equal to half m by V, we know m by V, mass by volume equal to the density. So half rho V2 square minus half rho V1 square plus rho g h2 minus rho g h1. So P1 plus half rho V1 square plus rho g h1. Let us group all the terms associated with the section A. So P1 plus half rho V1 square plus rho g h1 equals. Then on the right side we have all the terms related with the section 2. That is P2 plus half rho V2 square plus rho g h2. So so we can come to the conclusion that the terms, that is pressure energy, that is P plus half rho V square plus rho gh equal to constant. That means the sum of the pressure energy and the kinetic energy and the potential energy is equal to a constant. And this is the Bernoulli's theorem. Okay, so the sum of the pressure energy, kinetic energy, and the potential energy is equal to a constant. So we can have the statement of the Bernoulli's theorem, that is the sum of kinetic energy, potential energy, and pressure energy of an ideal fluid in a streamline flow remains constant throughout the flow. So this you can see this Bernoulli's theorem is in accordance with the law of conservation of energy. Okay, so suppose we have this tube, that is with a non-uniform tube, that is with a different area cross section. Suppose this tube is kept in a horizontal level, the same horizontal level, that is those 2 sections. The height for the 2 sections, that is h1 and h2, are the same. In that case, there is no potential energy difference. So we can the remaining terms, the pressure and the kinetic energies, that is P plus half rho V square equal to constant. Okay, so that means the sum of the pressure energy and kinetic energy equal to constant. So in that case, P plus half rho v square equal to a constant. Suppose if there is a region in which the pressure is increased, then automatically at that section the velocity of the fluid will be decreased. So according to that relation, the sum of these pressure plus pressure energy and kinetic energy should be constant. So if the pressure is decreased, then the velocity correspondingly the kinetic energy should be increased, so that the sum of these energies should be a constant. So for this relation we have so many applications. Let us familiarize with two applications of the Bernoulli's theorem. Here one is the atomizer. So atomizer, we are already familiar with the modified form of the atomizer. It's a body spray, or in spray painting, or car wash stations, etc. So the atomizer is a device to spray a liquid or make a liquid into a jet of tiny droplets. So the principle behind the working of atomizer is the Bernoulli's theorem. You know, according to the Bernoulli's theorem, the velocity of a fluid increases in a region, so the pressure decreases in that region, and vice versa, in order that the total energy remains constant. So let us see. Let us familiarize with the parts of an atomizer. The schematic diagram of an atomizer is given. The essential parts of the atomizer are a cylinder C with a piston P, a narrow T-section pipe, and a container to fill the liquid to be sprayed. So let us see. As we push the piston rapidly to inside, what will happen? The air in the cylinder begins to move towards the T-section. What happened? In the T-section, the area of cross-section is the since the area cross-section of the cylinder is larger than the area cross-section of the T-section pipe, as a consequence of the continuity equation, the velocity of air moving through the T-section pipe is greater than the velocity of air in the cylinder, because according to the continuity, we know A1 into V1 equal to A2 into V2. If the area is increased, automatically the speed is decreased. If the area is less, the speed is increased. So the speed of air particles, the air in the T section is greater. So then we are according to the Bernoulli's theorem, we know Bernoulli's theorem. If there is increase in velocity, there is a decrease in pressure. So according to the Bernoulli's theorem, the pressure in the T-section pipe must be lower than the pressure at the surface of the liquid in the container. Okay, so because of this pressure difference, the liquid in the container rises up and reaches the T-junction pipe. So the liquid mixes with the high-speed air, then it to form a spray. Okay, so that is the working of the atomizer. So if we make this end again become very narrow, then again according to the case of continuity, the velocity of the spray will be higher, and we can spray the liquid into very tiny droplets. Okay, so for a perfume bottle or a spray paint, the container with liquid is kept at a higher pressure with an air compressor. So a small pressure difference created due to the press at the spray piston will give a jet of liquid particles, or let us say atomized liquid. So this is the working of a atomizer. So this is a daily application, isn't it? So let us come to the next application, that is the airfoil. Airfoil is a special shape of solid objects which produces a lifting effect or floating effect while moving in a streamlined fluid or air. For example, the cross section of the wings of an aeroplane, boomerang, wings of birds, propeller blade, turbine blade, etc., is somewhat with an airfoil shape. What is you can see in the figure? What is the characteristics of the airfoil shape? It has a rounded leading edge that is followed by a sharp trailing edge and a curved surface. Okay. When such an airfoil is moving against a streamlined air, because of this special shape, the streamlines might have a speed difference at the upper and lower surfaces. You can see. So during the motion of this type of airfoil, so the air streamlines in the lower surface, they have to travel a less distance compared to the air streamlines in the upper surface. In other words, they have the air streamlines in the upper surface has to travel a longer distance compared to the air streamlines in the lower surface. So these upper streamlines has to travel very fast. So they have to move with a very high velocity compared to the air streamlines in the lower surface. So according to the Bernoulli theorem, so this upper surface, since the upper surface of the airfoil is a region of the higher velocity, then it will become a region of low pressure as compared to the lower surface, which has a high pressure. So you can see there is a pressure difference is created due to this the special design of this airfoil. Okay. So what is the net effect? Net effect is that there is a lifting. There is a lifting effect comes into action, and this lifting force from the lower side of the airfoil, which tries to float the airfoil while it is in motion. Okay, so this lifting effect comes into action only when the airfoil and the streamlined air are in relative motion. If it is in a static state, there is no kind of pressure difference created. Okay, so the lifting or floating motion of the paper plane or the boomerang can be understood with this Bernoulli theorem. And with this, due to the special design of the aeroplane wings, there is a lifting force is there that helps the aeroplane to fly forward, and it can save a lot of energy for keeping the mass at the air floating because of this airfoil shape of the wings.